Sampling Methods, Part 1. These three sampling methods all use an element of randomness in the selection process. We look at these three in Part 1. Moving on to systematic sampling, so this is where you select every 10th person or every 20th person in your population. So how do you know it's every 10th or every 20th? So that value n comes from a formula. It's your population size divided by your sample size. And again, there's some advantages and some disadvantages. An example, 2,800 students, we need a sample of 50. So I've done the population divided by the sample size. It gives me 56. That's a key value that we need to use. So I've numbered my population. I randomly select the first person in the interval 1 to 56. And then I select every 56th person thereafter. So here's the first block of 56 numbers. I'm going to select one person from there. Here's my second block of 56 numbers. I'm going to select one person from that block, and so on until I reach the final block there, and I'm going to select one person from this block. That gives everyone a 1 chance in 56 of being selected. And because I randomly select the first person, there is an element of randomness in this process, but this is not a random sample. As soon as you pick the first person, you know exactly who's coming next, and you shouldn't know that with a random sample. Now this is the same example with a slight modification. I've got 2,820 students this time, and when I do my calculation here, I get a decimal value. So how do you deal with a decimal value? So you could round up or you could round down. If I was to round down to 56, again, I've got my numbering scheme, and I want to randomly select the first person in the interval 1 to 56, because I'm using that value again in here, and I want to select every 56th person, again that value. So once again, here are my blocks of 56 students. There are 56 students here, there's another 56 students here, and so on. But if you look at the very last block, this one, there's only 20 students in this one. So if I'm selecting one student from each of these blocks, then all of these up to here have a 1 in 56 chance of being selected, but not in here. So there is an unequal chance of selection this time for the population. So if the first person selected was student number 56, who would the last one be? So I've got one already. I need 49 more in my sample. Here's a quick calculation, and it's showing us the last student selected would be student numbered 2,800, which means anyone in this interval would have no chance of being selected at all. This is because our step size is a little bit too small, and as we go through the population, we're not really making progress going through, and we never reach those who are at the end. Now what about if we round up? So we're rounding this number up to 57. So I randomly select the first person in the interval 1 to 57. I'm using this value everywhere now, 1 to 57. I select every 57th student. So now I've got blocks of 57 students. 57 students in here, 57 in here, 57 in here. So once again, if this is my first student selected, student number 57, I need 49 more to get a sample size of 50. Who will the last one be? So this calculation shows the last person selected would be student number 2850. Now 2850 here doesn't exist. That was my last student, 2820. So what you could have potentially here is an equal chance of being selected, 1 chance in 57, because every block has 57 students. However, you may end up with a sample of 49 students, or you may get 50 students. And if you have a large sample, it doesn't really make much difference. So given a choice, it's better to round up. And it's not about rounding to the nearest whole number. And you have to use a whole number for n. We've got discrete data, individual students. We can't go up in a step size of 56.4, it's ridiculous. We need 56 or 57, and rounding up is better.